Let's resume. So we set up the stage for doing the first attempt, making approximation towards the helium ground state problem. We have set up the stage for doing first order perturbation problem. But as you will see later on in this section, there are a lot more than just first order perturbation. So a lot more. So here, for completeness, I write down the helium atom Hamiltonian again. Now in the form to prepare for doing perturbation. The first four terms we just discussed is the exactly solvable part H0. Then this term is the term that we are going to do perturbation upon. For completeness, I copy again the ground state wave function for this H0 part. It is a 2-electron problem, but separable. Therefore, the ground state wave function multiply into each other, but one for number 1 electron, another for number 2 electron. Z is 2 for our hydrogen-like problem. Therefore, this is the 0th order wave function. The 0th order ground state energy corresponding to H0, we just solve it. It is minus 2 Ha3 plus minus 2 Ha3. It is minus 4 Ha3. Okay? So we know everything now for the 0th order problem or the unperturbed problem. So we look into our toolbox, first order perturbation. That's the simplest thing one can do, but it turns out it's not so simple and integration to carry out. So we can write down the formula for first order perturbation theory of the ground state energy correction immediately. So following our standard notation, we are looking for the ground state. This is the first order shift in energy. 0th order, we know here, okay? So the first order is the perturbation in the middle, the unperturbed wave function, 0th order wave function on the left, on the right, and integrate over all variables. But in our problem, we have 6 variables to do, 2 particles. Therefore, we have to integrate over x1, y1, z1 for electron number 1, and x2, y2, z2 for electron number 2. So this is a 6 variable multiple integrals to do. After you do that, it is an energy. It's a number because both R1 and R2 are now integrated over. Okay? Now we plug in this form because we know each form. Okay? So to write down that form, it is equivalent to the 0th order wave function is a product of single electron states. So I plug it here. I plug it here. So we have equation 17 to calculate. So everybody, do you understand these 2 expressions? Turns out to be important later. Is that okay? Okay, good. Now, so the remaining thing is first to see what is the result of doing this calculation, okay? In this week's exercise classes, the TA will plug this thing in here and there and do the integration for you. The answer is very simple, but the process takes maybe 2 pages. But each step is an elementary integration, meaning is the thing that you know how to integrate. Sine theta, cosine theta, things like that, okay? So it's doable, but very long. Rather interesting to know how to do it, actually, especially for the mathematics major. So you may wonder why we are doing such a complicated business here, 6 variable integration, okay? So first of all, that can be done. TA will do it for you, don't worry. You are not expected to know how to do it offhand, but it's a good exercise for you nonetheless. But we are doing it here for a good reason, because after we do this exercise, some big concepts come out. It will lead to the second approach, the variational method. And when we do that, that gives us immediately a big idea of how to include the effect of the other electron into the equation of a single electron. The idea behind screening. Roughly speaking, we have 2 electrons, but we don't want to handle that. We want to handle single electron wave functions. But what is the effect of the second electron, the first? So the second electron lives around the region of surrounding the nucleus. So it looks as if it has an effect on this 1 electron that we are focusing on. So this electron is screening out part of the nuclear charge. So what it sees is not plus 2e anymore. It may be plus 1.735 charge. That is a screening effect. That comes out from the variational calculation rather nicely. And then if we extend this variational calculation further, that will take us to the next topic called the self-consistent Hartree method in quantum chemistry. So that is why we are doing it here, okay? So don't feel uncomfortable when you see, oh, so complicated thing, why we want to look at that, okay? We have good reasons. So let's write down the integrals. So I plug in the wave functions. There are 4 terms. This on the left and on the right, okay? But they look the same, okay? So therefore, I group them together. So I plug in the first part. I want you to follow more closely. For the first expression, I use this form without substituting Z equals 2. But on the second equation, I will use this Z equals 2, all right? So therefore, you see 2 expressions. This one is in terms of Z. The second one, I plug Z equals 2. So this is the integral that the TAs will do for you this week, okay? So go to exercise class and they will, you know, let them show off their skills, okay? They will be happy to do this, okay? So for our purpose, don't worry about how to evaluate this particular integral. The fact is that this can be done analytically. I mean, this thing can be evaluated exactly. So after doing that, if we keep the Z in the calculation, this is the answer, okay? And then you may wonder where this M comes from. It is hidden in the bore radius, okay? So this is the end result of equation 18. We call that this thing is one Hartree. This is half the hydrogen ground state absolute value. The minus sign is taken out. So I can call this simply 5/8 times Z in Hartree. The symbol for Hartree is E Hartree, the subscript EH, okay? So now let's look at how it works. Does it work? We have the ground state energy minus 4 Hartree. Now, first order shift is this amount. So total up to first order perturbation, this is our prediction for the helium ground state energy. So let's look at the picture again. Zeroth order, ignoring the interaction, is very negative. This is the zeroth order. This blue thing is the actual, the target that we want to get at. This is minus 79 eV. In Hartree, it is this metric number, minus 2.9033 Hartree. So after we did the first order perturbation, we have a plus 1.25 Hartree. Therefore, it is together minus 2.75. If we put it into EV, it's minus 74. Okay, so first order perturbation has taken us from here up there. Okay, now first of all, you must appreciate it seems to work not too bad, right? So the difference now is much smaller, 5 eV or so, 4 eV. Okay, now secondly, it takes us above the actual thing. Now that is a good sign. You know, first order perturbation, you can take it as a stupid variation calculation, right? You have nothing to vary. You just assume this is the trial wave function and then do the expectation value. The variational calculation principle says it must be higher than the actual one. Ah, good. Now it is higher than the actual one, okay? So when you see that, this is a good sign. So Mr. Choi, that was the question you asked. Okay? All right. So first of all, we are still off by something, but we are not that off now. Okay? So let me conclude. The first order calculation give us okay result, not too bad. But more importantly, it already hinted at another calculation that we could try, and it's very worth trying. It is a variational calculation. The end result will bring out some idea about screening. We will do that in a while. Last remark, you may think, how about second order? Well, you may want to try it, but it's quite difficult to do the integrals, let me tell you, okay? So that's why we will stop here, because this calculation has a greater meaning in terms of directing us to the variational calculation that follows. So here is the and more part of this section. Remember, I say first order perturbation and more. Okay, this is the and more. So it's here we will try a variational calculation. It's a very clever and important traits of the first order perturbation calculation that we did. So let me motivate it. So for completeness, I write down the helium atom Hamiltonian again. This is the problem. We want to find the ground state. The second line is just some decoration. It is the same as the Hamiltonian written down here. So what have I done here? I write down an extra term with the Z here. Okay, so I have a minus Z squared something term, but I subtract it, I cancel it out. So do you see that I have a plus Z, also the same thing? Okay, so all in all, if I cancel off the common term, this thing is exactly that. Do you see? I haven't done anything bad. I'm just adding a zero. You understand, guys? This turns out to be a key step. Okay. Similarly, the problem is a -2 here. I did that for the second term. So I've done nothing. It's the same helium atom Hamiltonian. But now it is the important trace. Okay, the trace is like this. This is an identity. Therefore, Z can be any number. It's right. I add it in, I subtract it out. I add it in, I subtract it out. I haven't done anything. Therefore, Z doesn't carry the meaning of the atomic number anymore here. We can take it as a variational parameter. All right. Now you may wonder, the variational parameter should go into the wave function. You are absolutely right. I'm writing the second line just to help those students who want to do the calculation by yourself. That follows. Okay. I'm going to claim the result without deriving it. If you go to the exercise class this week, you know how to do that 6 variable integral, and then you can come back to work out this variational calculation with the same technique by yourself. Okay, and then the second form will be much more convenient when you do the variational calculation. But the point here is this Z can be any number, right? It could be 1.5, it could be 1.7. Because I add it in, I take it out. I add it in, I take it out. It doesn't matter, right? Now, what is the trial wave function? Again, when our idea of doing this multi-electron atoms is to try to write the many electron wave function into products of single electron wave functions. That is to say, each part only depend on one electron coordinate. R1 here, R2 there, separately. So we form the product. So we are motivated by this form. Okay, without regarding the Z being equals to 2. I use this as my trial wave function and using Z as the variational parameter. So I copy this thing here. So this is why I wrote 2 forms in the previous pages to set up the stage for this calculation. So this is my trial wave function for the ground state. I'm using Z, one variational parameter only. Okay, so now the game is very clear. Evaluate the expectation value. So this thing, the whole thing in the middle, and this thing integrate over 6 variables. Okay, So after that, you will get an expectation value that is a function of Z. You vary Z to minimize this expectation value. Then we will have hopefully, a better estimate of the helium atom ground state. Okay, pause here. Understand? No new physics. Old tools. Any questions? Okay. As the variational parameter, I use Z. Very humble, only one variational parameter. Okay. Now, I hope that you gradually appreciate, knowing a little bit technique, perturbation, variational calculation, you can do a lot of things. Okay. So stay tuned. Let's look at the result. So the calculation goes as follows. You take the whole Hamiltonian in the middle, use the trial wave function on the two sides, integrate over 6 variables. I should put 2 integral here to make sure that you understand there are 6 things to do. Okay. The lovely thing is that it can be done analytically. Well, that is not surprising if you know how to do the first order perturbation. And the answer is, the expectation value is this much H3. Okay, so again, if you want to know more about atomic units, read the 2-page appendix. I have 2-page appendix introducing this set of units. One student asked if I am introducing Z into the Hamiltonian. The answer is no. I'm using this as the Hamiltonian, but I'm saying this is exactly that mathematically. Okay, but using this because for some students who want to do it by yourself, when you use this, operate on this, this is a ground state of a Z charge hydrogen-like state. The answer is no. All right, so that will make life easier. Okay, so this is the answer. Okay, but we are not done yet. We have to get the best value of Z, the parameter. Okay, I shouldn't have an S here. It's the best value of Z. Then I take the derivative, set it to 0. That will be my optimum Z value, and it is also analytically done, 27/16, or a rather bad number, 1.6875. I would like to stress that, take a look at that, okay? It is not 1, it is not 2, it is a fraction, well, a rational number, 1.6875. Okay, rather funny thing. All right. Now, we will interpret this Z star, the best optimum value of Z, a bit later. Okay. So let's estimate the best variational ground state energy. We plug the optimum value back into the expectation value expression. So this is the estimate. Plug it in, we get this number, minus 2.8477 H3. Okay, now immediately you see it is better than the first order perturbation result, right? Now, first order perturbation is here. Okay, minus 2.75 something. Variational calculation, we bring it down to minus 2.8 something here. The actual is minus 2.9, all right? So we are getting closer, you see? Okay, so at least we see better and better sign. Our toolbox can actually zoom into the right value after we do this, do that, okay? But at this point, the physics turns out to be more important than the calculation, the numbers, all right? Because a physical picture of the screening effect start to emerge. The point I want to make is this optimum value Z star. Remember, our trial wave function has a Z in there to play the role of the variational parameter. After we did the calculation, the best value is a funny number. It is not +2. If the electron only sees the nucleus of a helium atom, it is +2e. However, when we use the idea of the trial wave function is a product of what electron number 1 wave function times electron number 2 wave function. After doing that, this thing originally playing the role of what is the charge it sees, electron number 1 sees, takes on a funny value. It is smaller than +2. Okay, so now we are going to interpret this physically. Now, this part is the wave function, single electron wave function of describing what electron number 1 feels, sense in its living place, in the surrounding of the nucleus with the second electron in its vicinity. So what it says is that electron number 1 feels, no doubt, it sees a +e, +2e nuclear charge. But effectively, it doesn't see the full +2e, but it only feels a net positive charge that looks like a number that is less than 2. So it is +1.6875 after our calculations. So this must be due to some effect of the electron number 2. Right? So in conclusion, what electron number 2 does to number 1 is to screen out part of the +2e charge of the nucleus, so that what electron number 1 sees is only part of that +2e charge. It becomes this. Okay? So we can think in similar terms to interpret the second term. What electron number 2 feels is that it sees the full +2e of the nucleus, but electron number 1 has the effect of screening off part of that +e charge. And electron number 2, again, only sees a net charge like this. Okay? So this is the key concept. To understand how to interpret this result, because there's a lot to follow from it. Is that okay? May I? Okay. Again, let me repeat, we are stressing the idea, the concept. We are not going to do serious calculations for many electron atoms. It's too difficult to do it, okay? But as year 3 students in physics, that may be the first encounter of your study on electron-electron interacting systems. And many of these concepts carry over to solid-state condensed matter physics, okay? So we have this new idea emerging from a very simple variational calculation method. So what it says is the following. So this is the picture. I'm not good at drawing, but I try to make a cartoon out of it. So if there's only electron 1 alone seeing the nucleus, it will see this whole thing, full 2e charge. But it's not the case. What electron 1 sees is the effect of the nucleus plus electron number 2. What electron number 2 doing is that it has a single electron wave function is spreading itself around the nucleus, and it is negatively charged. So in effect, what electron number 1 sees is not the full plus E charge, but it sees the nucleus effect plus roughly some effect, which is repulsive due to electron number 2. So these two can add up to an effective charge, which is 1.6 something, okay? That looks something like that. And then the most important thing is that if we take this picture focusing on one electron, the other electron in helium or the other electrons in the lithium onward, the other atoms, they can contribute effectively a single electron potential energy function. Thereby, if we focus on one electron, it started to make sense that we can reduce this complicated multi-electron atom problem into single electron problems by including the Z-1 electrons effect into an effective potential energy function acting on the one electron that we focus on. That is the key concept emerging from this discussion. So conclusion, the variational calculation using the thing as a child wave function supports the following idea. It is possible to reduce the complicated problem into single electron problem. And the single electron feels two things. The nuclear charge, no doubt, that is attractive, but the remaining Z-1 electron also provide an effective repulsive term on the one electron that we focus on, okay? So this is the educational value of this two exercises. First order and then the variational, they go, conceptually following one line. Final remark. What we have done here, this idea of reducing complicated problem into single electron problem, but including the other electrons effect in a kind of approximated way, is applicable to many problems in atoms, molecules, and solids. The remaining question in those subjects is how well we can turn this problem into a single electron problem, and then how to fill the electrons back into the single electron states, and then what to do if we want to do a little bit better than this approximation. the last question gives rise to a big separate subject called many-body physics. So here, I would like you to go to the atomic unit appendix if you want to know more about what atomic units is about. But for our purpose, very simple. A hard tree is 2 times 13.6 eV. That's it. So we have a good starting point. Then we move on more implications of the particular 6-dimensional integrals that the TA will do for you this week. It turns out that there is big physics behind this integral. And after we understand this big physics, a very important consequence comes out, which is, I already mentioned, the self-consistent calculation called the Hartree method. That is a method to calculate the single electron state, the phi 1s that we wrote down. So what is the integral and what we want to interpret? So let's look at it. So for completeness, again, I write down what I wrote down in the previous pages again here. So we have done 2 calculations. In the first order perturbation, the ground state energy is written as a product of the hydrogen-like 1s, and this phi s takes on a known form because we are doing perturbation. The unperturbed Hamiltonian is defined. Therefore, this is known, okay? But motivated by that, we also did a variational calculation in which this trial wave function carries a z to be determined, okay? So therefore, if we think about a trial wave function in general, I could always write down a trial wave function for R1 and R2, thinking about the ground state, they must be in the same state. We have spin up down yet, right? So don't worry. But leave this as an unknown function to be determined, okay? So either way, we will have to do the following expectation value of the Coulomb repulsive term between 2 electrons. So the integration that we need to do is on the left, on the right, this thing in the middle, okay? So let me call this integral J. That is a common symbol in atomic and molecular physics. To be more explicit, electron number 1 is in something called the 1s. Electron number 2 is also in 1s. I label it as 1s, 1s. Sometimes I'm lazy, I just call it J. So that's why I put that here, okay? But more formally, I would like to, follow number 1 is in 1s, number 2, so there are 2 states involved, okay, in general. So this is the integral that we want to interpret. Notice that the interpretation doesn't rely on whether we know the form or it is a yet to be found function, okay? It doesn't matter. So look at this. There's a E square. I would like to write E square into minus E times minus E because it is related to electron Coulomb repulsion. So therefore, it is the same thing, 26, no new thing. I'm just writing this as minus E times minus E and give minus E to this times that. That will be phi 1s R1 square. Okay, similarly for the other term. So therefore, I will write it as such. Sorry, I missed the D. No, it's okay. Here, okay. So it's correct. So I have this for phi 1SR1. I have this for phi 1SR2. Okay. Now, these are single electron wave functions. Therefore, let's interpret what is in this bracket. This thing is the probability of finding electron number 1, R1 here, the 1, electron number 1, in the position R1 in a tiny box, so-called volume element, but just a tiny box of this size. Okay, so quantum mechanically, this is the probability of finding that electron there, and times minus E is that bit of charge due to electron 1 at that location. So formally, the first bracket, I interpret it as that. So I pause here, that is the key point. Is that okay? Okay, good. Similarly, if you take that in, the second term means the same thing, but only for electron number 2 at a different location, R2, right? In a box there. And the denominator is the same, the 4.000, okay? So I'm interpreting the integram. Do you see it's the same thing as a bit of charge at one place interacting with a bit of charge of the same sign in another place, and this is the Coulomb repulsive potential energy. Okay? So let me summarize. This integral in first order perturbation of the ground state energy has a classical electromagnetic interpretation. Okay, that's the point I want to make. All right. So, you know, another cartoon way, I have a nucleus. If I think about the first term, first bracket, it is about electron number 1. The bit of charge here is given by this bracket. I don't want to plot it on the same graph, so this is the same nucleus. Okay, and then for the second electron, electron number 2, that is the bit of charge represented by there. This bit will interact with that bit. If I plot it together here, will be here, okay? And then the Coulomb interaction energy will be like this. So this is the classical electromagnetic interpretation. But then the charge is spread out according to the wave function, thereby I have to integrate over everywhere. They can be at different places, okay? So pretty nice. This integral that the TA will do for you, there's an answer for that, okay? Can be interpreted in a classical electrodynamic sense. Let's generalize this interpretation a little bit. So if I don't have 1s and 1s, but state A, a state B, that could be different. The previous case, they are the same, but they could be different, say. I can still carry out the whole interpretation with no trouble. So thereby, this interpretation, electromagnetic interpretation, can be carried out even for A state and B state being different. That will be the case in one situation, like a helium excited state. For example, one electron in 1s, one electron is to be called in 2s. All right, so you will have A being 1s, B being 2s, and they are different. Nonetheless, the interpretation that we carry out works through every step in the argument. So no problem. We will not make use of this at the moment, but I would like to introduce the name of such an integral. This integral, together with this integral, J, they are called many names. Coulomb integral, obviously, because classical electromagnetic interpretation. They are called direct Coulomb integral with an adjective direct, or simply they are called direct integral. Okay, then you may wonder, especially this thing, is there an indirect Coulomb integral? The answer happens to be yes. And that indirect Coulomb integral does not have a classical electromagnetic interpretation. It is entirely quantum in nature. We will see that later when we make a discussion on the helium excited state. But in the ground state, we only have 1s, and thereby we only have this direct J term. What is the indirect Coulomb term? Let's look at why we have this classical interpretation. All in all, we see this thing square. That is to say, we have two things that they are of the same state, first of all, and they have of the same argument, so that they can multiply together to give us this probability density minus times minus E, that will be the little bit of charge. So we need this appearing to have this classical interpretation. Now, I would like to write down the very strange so-called indirect Coulomb term for you here, but you don't know where it comes out at this point. Later on, you will see. So this is the thing that I will call K, well, that is called K in the literature. This integral is related to two different states, A and B. Now, look at this funny thing. In one color, so I have this R1 thing here. So on the left-hand side of the integral, it is in state A, but on the right-hand side, it is in state B. Similarly, for the R2, this side is in B, this side is in A. So nowhere you can find such a product. Nonetheless, it is no more, no less, 6-dimensional integral. You do the integral, you will get an energy out of it. Okay? Now, this is what the indirect Coulomb integral is about. A more common term, this is called the exchange integral or the exchange energy. For those who know a little bit of magnetism in the class, that is the origin of magnetic properties of matter. This particular integral, it turns out to be a very quantum effect. Okay? But at this moment, I just want you to realize that there is indeed something that of the similar form, but one cannot find a classical electromagnetic interpretation for such an integral KAB. Okay, so I think I should stop here Next time, we will make a second interpretation of this same integral. Okay, so this is the same integral, but written, grouping some term. What we are trying to argue is that when I look at this integral in this way, it looks as if this is the extra screening effective potential energy function due to electron number 2 on electron number 1, because it is just an expectation value here. Okay, so once we grab this and write down a Schrödinger equation, very interesting thing comes out. We have a Schrödinger equation. We want to solve for this thing, but the potential energy function rely on the answer. From that point on, you need to do numerical iteration to get a self-consistent answer. And that is called the Hartree approximation. And that's the beginning of the whole chemistry industry. Okay, so I will explain this a little bit more on Thursday. So that's all for today. I will stay around. If you have questions, you are welcome to ask.